we're going to be looking at in this chapter all about bonding. And we wanted to start off and refresh your memories on the different types of bonds that could form. So one quick thing that I want to point out the difference between is bonding, which is our current chapter, and intermolecular forces, which is what's coming next. Bonding is where you're focusing on one molecule or one formula unit and looking at the attractions between the atoms or ions inside one. Whereas intermolecular forces, our next chapter, is where you have two or more atoms or molecules or ionic substances, and you're looking at the attractions between multiple particles. Those particles could be the same thing, like you see here in the water molecules, where I've highlighted these blue dashed lines. Those are the attraction from one water molecule to a neighboring water molecule. Or the chemicals could be different. So like here we've got a water molecule with a different chemical, and there's attractions between those different chemicals as well. So basically, intermolecular forces, you need at least two separate particles, and you're looking at the attractions between them, where bonding is you're looking at one particle only. Okay, so there's 5 different types of bonding that we're going to look at in this investigation: polar covalent, nonpolar covalent, ionic, metallic, and network. And just wanted to go through some basics with you. So in that ionic versus covalent, 2 big categories. Your ionic ones are always made up of a cation with an anion. Metals typically lose electrons during chemical reactions, so they form your cations. And nonmetals tend to gain electrons during reactions, so they're your anions. So if you look at a chemical formula and see a metal-nonmetal combination, you know it's going to be ionic. Covalent molecules tend to be made up of nonmetals only. Occasionally, you might get a metalloid with a nonmetal that could be covalent as well. There is no such thing as a metal-metal compound, so you won't see any of those. When you look at number 2 here, our metals, those are the easiest ones to spot: copper and aluminum. Just in case you don't remember, the metals are to the left of the staircase line on our periodic table, and the nonmetals are to the right. Metalloids are the ones that hug the stairs. Everything except aluminum. We call him a straight-up metal. When you look at covalent versus ionic here, my ionic ones, the sodium chloride has sodium, a metal. Sodium bromide has that sodium again, a metal. Everything else is made up of nonmetals, or in the silicon dioxide case, silicon's a metalloid, so the rest of those guys would be covalent. Soluble, insoluble means things dissolve or don't dissolve. You learned during our periodic table chapter, electronegativity measures how well an atom can attract electrons to itself in a bond. It has to be bonded to something else to have an electronegativity value. And we learned that fluorine has the highest electronegativity pattern, while francium has the lowest. Fluorine has a high effective nuclear charge, lots of protons, and a small radius, where francium has the low effective nuclear charge, large radius. So if you think about it from a Coulomb's law perspective, fluorine would do a really good job at attracting electrons, while francium would not. For the polar, nonpolar bonds are where electrons are shared equally between both atoms in a bond. So I like to give the example of you and your friend go out for pizza. You eat half, they eat half. You're sharing the pizza equally. What that means in terms of bonding is that the electrons spend 50% of their time around, if you had like a carbon bonded to another carbon, they spend 50% of their time around the left carbon, 50% around the right. If you have a polar bond, you're sharing your electrons unequally. So an example there, if you have an oxygen bonded to a hydrogen, oxygen has a much higher electronegativity value. So he's kind of the electron hog. He's the pizza hog. He eats most of the pizza, where hydrogen with the lower electronegativity value doesn't eat as much pizza. So the electrons spend more of their time around the O than the H. So they're still sharing the electrons, but it's not an equal split.